they couldn't see anything. All right. So what we are doing today is one of my favorite topics from Calc BC. It is called integration by parts, and it's a beefed up u-substitution is probably the best way I can describe it. We are now going to be getting into even more integrals that previously we could not solve, and integration by parts is going to allow us to do a lot of them. And it also allows us to kind of learn about some other things. Like one of the questions today, we're going to learn how to integrate natural log, and integration by parts allows us to do that. So the first example is this one here. It looks like a very easy integral because it's just x times sine of x. But the problem is that it's impossible for us to solve this with u-substitution, because if we let u equal x, well, then du is 1 dx. We can't do anything about sine then. And then if we try to change this into u being sine of x, du becomes cosine of x dx. Still can't really do anything. We could turn this into arc sine of u equals x, but that's not making this easier at all. That's just turning into a different form that's probably worse than what we started with. So what we're going to do then is we're going to use this process called integration by parts, and that will then allow us to integrate. And this is the formula. And you're probably going to hear me say this quite a bit as well. If we were to rearrange the letters in this box, you're going to hear me often say of dove. That was the phrase that my calculus teacher used all the time. He probably regretted it, because then he got to the point where he'd ask us, all right, what are we supposed to do to solve this? And we'd say, we of dove it. And he would kind of groan and be like, yes, we're going to do integration by parts. But I mean, that was his fault for teaching it. And so likewise, it's going to be my fault now that I taught you to say that as well. So anyway, what's going to happen is that we have an integral, and it's going to be two functions multiplied together, just like the last example was x sine of x. So we have f of x and g prime. And what we're going to do is, instead of just a u substitution, we are also going to do a v substitution. And specifically, here's what I want you to be looking for. You're going to let u be equal to f of x, and you're going to let dv be equal to g prime of x dx. And I'm just going to make a note here to the side. We want to do the circled parts first. Once we have identified u and dv, we integrate dv to find what v is, and then we are going to find the derivative of u to get du. And so the last part that I have is down here, which is really important. This, if it's confusing, I promise you, once we start doing some examples, you'll start getting the hang of it. F of x should be easily differentiated, and it has to have a finite number of derivatives. So in other words, what we need to do is, it's easy to get the derivative. And we only need a couple derivatives at most. Oops, sorry. So that's what that part is telling us. And then the bottom part here, so g prime should be easily integrated, or in other words, easy to get the antiderivative. I can't spell derivative. derivative. There we go. Kang, I don't know if I'm ready for the pineapple pen guy. He's posting stuff in the chat there. So, I will admit this is a lot of information here. So I think it becomes easier to understand once I'm able to do a couple examples, and then you can get the hang of the process for solving these. Does anybody else need more time for this, or can I move on? Okay, I think we're good. So going back then to that initial example that we had, we're going to integrate x sine of x. So a couple things that we need. First, we need to remember the equation. So of uv minus the integral of duv, or technically it should be v du at the end, but you can't spell of when it's v du. And then we're going to start by identifying what is u and what is dv. So again, as a reminder, u should be something where the derivative is very easy to find, but we don't want to have to do it an infinite number of times. So while it's easy to do the derivative of x and it's easy to do the derivative of sine of x, we want to pick the one that can be done the least number of times.
X.
Yeah, exactly. So sine of x has an infinite number of derivatives. We'll never stop. So let's let u be equal to x. Therefore, dv, something that is easy to get its antiderivative, will be sine of x dx. Now that we've identified those two, we can move on to du, which is easy. The derivative of x is just dx. And then we can move on to v. Now, we want to do the simplest antiderivative. So what that means is that we will not have a plus c. We're just going to let c be equal to 0. So the simplest antiderivative of sine, it is negative cosine of x, but like I just said, no plus c. We're just going to pretend that it's 0. Now we're going to use the equation of dov to build the new expression that is equal to this.
Mr. Briz.
Yeah, what's up?
Why is dv equals sine of x? Can you say it like that again, please?
Oh, yeah. So we started, I'm going to hide both of those for now. And we know that we start with u and dv. The rule for u is that we're going to have to find a du. And since that's the derivative, x, sorry, let me rephrase that. Since du is the derivative of u, we want the function for u to be something whose derivative is easy to find, but also we want to avoid it being an infinite number of derivatives in case we have to do this multiple times. So the problem with letting this be equal to sine of x, although the derivative is easy because it's cosine of x dx,
it's like
yeah, what will happen if we then put this into the equation of dov, oops, dx is at the bottom. If we did it like this, the problem that we would run into is that this, it couldn't be solved. And let me actually just demonstrate. If we did it this way, we would get sine of x times x squared over 2. So that's the uv part. And we need duv. And we would get x squared over 2 times cosine of x dx. And the problem is this integral here. That's not easier for us to solve. In fact, that's actually more complicated than what we started with.
Oh, okay.
Yeah, so by doing it this way, I've discovered that we should not have let u be sine. We should not have let dv be x. So that's how I knew then to make dv be sine, because if I now show you, I'll just, I guess, what am I doing? I guess I could just erase everything. So if we go back then to what I originally had, so we had u was x, du is dx, we had sine of x, and then v is negative cosine of x. So now if we use of to write this, uv will be x times negative cosine of x. And now duv is going to turn into something much nicer for us. It's going to be negative cosine x dx. And this looks a lot better than when we had u and dv switched. Because now we're able to integrate that integral at the end. And this turns into negative x cosine x plus the integral of cosine x dx. And there we go, we're done. Because it's plus sine x and then plus c.
Nice.
So what used to be an impossible integral for us to do, even with this new method, it turns out there's not a lot of work involved to solve it. It's just some different work. Is it okay for me to move on?
Miss First, I
Yeah,
have a question.
Yeah.
Does this one work in the chain rule?
What do you mean? How does it work with the chain rule?
I'm like this one, but like the function behind, like with the chain rule. So like, is this like still like the same?
Oh, so like if we had sine of x squared?
Yeah, kind of like that.
Yeah, we would be able to, we can do this with chain rule as well. The questions will get more difficult, and I think the ones after this will be more similar to what you're asking.
Okay.
Yep. Were there any other questions then with this before I move on? No? Okay. So again, still keeping it as pretty basic for us. So we have x natural log x. Once again, we want to start with u and our dv. And this one is included because I guess I'm being a little mean here. Instead of giving you an easy one, I've taught you how to do this, and now all of a sudden I'm like, oh, by the way, I'm going to trick you. Initially, you would probably look at this and say, oh, well, the last question, u was equal to x, so let's just do that. That means dv has to be natural log of x, and we're on our way. Okay, well, du, that's fine. We know that's dx. But some of you looking ahead probably realize we have no idea what the antiderivative is for natural log of x.
Isn't it 1 over x?
That's the derivative, but that's not the antiderivative.
Oh, yeah.
Yep. So I did tell you at the beginning of the notes, eventually I'm going to show you the antiderivative for natural log. But for right now, we still don't know what it is. So that means that this actually is the wrong way to set up this question. Instead, it may seem counterintuitive, but we're actually going to let dv be equal to x dx, and u is going to be natural log of x. And I think some of you might be thinking as well, the issue with this is that you thought, and I told you, you was supposed to have a finite number of derivatives. Like Miriam said, we're going to get 1 over x. But the issue now is that actually would go on infinitely if we kept doing more and more derivatives. That's never going to stop. But I noticed that when I do the antiderivative for this part here, the dv, and we get x squared over 2, I'm looking at this now, and I realize something's going to cancel. And that is going to help us out when we set this up. So once again, here's our equation of dov. So uv will be natural log of x times x squared over 2. We're going to do minus. And then we will get 1 over x for du. V is x squared over 2. And we get dx. And just like I said, our integral is going to be able to cancel some things out. So we can get rid of the square. We can get rid of the x in the denominator there. Now what we'll have is in the front x squared natural log of x over 2 minus, and then we will get x over 2 dx. If you want, you could factor out the 1/2 from the integral. We don't need to though. And when we integrate now, what we're going to get is x squared over 4, and then plus c.
Mr. Bruce.
Yeah, what's up?
Okay, so like when we decided that natural log of x is going to be u, can you explain that reasoning again? Because
yeah. So what happened was, here, I'm going to do it down here. So what happened there was that I originally said I'm going to let u be equal to x because I know that the derivative of x is really easy. It's just dx, or 1 dx, I should say. But the issue that we ran into was that required dv to be natural log of x. And the problem is that we have not learned how to do the antiderivative of natural log. So we have no idea what v is, and therefore it's impossible for us to do this question. So because of that, that's why I knew that I had to switch these two, and I guess get rid of that dx. But
so are we ever going to learn the antiderivative for natural log?
yeah, it's actually right there.
Oh, okay.
Yeah.
Wait, Mr. Briz, I have a question.
Yeah.
So after we learn the antiderivative of natural log, will it be easier to use that or still keep like solving the problem like this as you did here, where u is equal to natural log of x?
Because the antiderivative for natural log of x is not super easy, it might, I would say that the way that I did it up here is still preferred.
Okay.
Maybe what might be useful, everybody, is if I just show you right now what would be the antiderivative of natural log of x, just so you can understand why I solved it the way that I did. So like I was saying before, we always want to start with u and dv. Now, just from that last question, we already know don't put natural log of x there because, well, the question is asking us what's the antiderivative of natural log. We don't know it. If we did know it, we could put it in for dv. And actually, if we knew it already, then we wouldn't even be having to do integration by parts. We would just write the answer. So for this question, yeah, go ahead.
So like, so that's probably going to be natural log multiplied by 1. Is that like what it is? Is that like what v is? Is v 1?
You're close. dv is 1.
Oh, okay. I got
Yep.
it.
So we're going to let u be equal to natural log of x, and then dv is going to be 1 dx. So then that requires v to be x, and then du will become 1 over x dx. So then we are going to use of. And that means that we will have u times v is natural log of x times x. Minus, and then the integral of duv. And of course, in that integral, that's going to cancel and just become 1. And so the integral is not too bad. Actually, it's quite easy, I should say. So the antiderivative for natural log of x ends up being x natural log x minus x plus c. And I'm going to quickly go to the Thomas book. You don't believe me on this. But in the brief table of integrals, brief, so you can't see me do air quotes, so you're going to see me write it there onto the screen. Let's see. I'm going to tell you which number it is back in the Thomas book. Of course, now the tricky thing is actually finding it in the first place. Here it is. Number 116 in your brief table. It says integral of natural log of ax dx equals x natural log ax minus x plus c. So there you go. So the Thomas book confirms that we have this correct. So yeah, now we have the antiderivative for natural log of x. And so you can see, not that it's the most difficult thing in the world. The antiderivative actually isn't that bad for natural log. But at least coming back to this example from earlier, I would say that that's certainly more difficult than when we found that the original v was x squared over 2. So I think the work in the other way isn't that bad, but I still think that what we did to solve this in the first place ended up being, I still think that would have been simpler than if we had tried letting natural log, oh sorry, I fixed that one already down there. I think that would have been easier than trying to solve it with natural log being dv over here. Does anybody need me to show the antiderivative for natural log again?
No, we good.
No? Okay. So what I want you to do then, let me get these out of the way. So I want you then to try this question. So use integration by parts or use of to find the antiderivative for that. I don't know how nice the answer is going to look, so maybe if you want, you can try typing your answer in the chat, or you can just wait a couple minutes and then I'll show you how to do it.
Mr. Briz, what's the Pythagorean thing for secant? Or do we have to not use that? Or
No, you don't need to use the right triangle for secant.
I know, but like there's like a no, like it's like something.
Oh, the Pythagorean identity.
Yeah. Or is that not
one-
going to help us?
That is tangent squared plus 1 equals secant squared, but that one is not necessary for this.
Oh, wait, so then what's the antiderivative of secant squared?
It might be easier if you think of your derivatives of the trig functions.
Okay.
So instead of trying to figure out what is the antiderivative of secant squared, maybe think of derivative of what makes secant squared.
Okay.
I'm not ignoring you, Miriam. I'm trying to answer to somebody else first. Okay, so what you should have seen here, kind of like the other ones that we've done so far, this is one where we do want u to be equal to x. And then for dv, that's going to be secant squared. So you are required to remember what the antiderivative of secant squared is for this. So du is dx. What's the antiderivative for secant squared?
Tangent.
Tangent, good.
Tangent.
Yeah. Is there a cat meow there? Anyway, I guess I shouldn't complain. There are pipes rattling in the bathroom just across the basement here for me. So I myself have weird noises going on in the background. Anyway, so from the equation then, uv minus the integral of duv. Then we know that we're going to start with x tangent of x minus, and then duv is going to give us tangent of x dx. So the antiderivative for tangent is one that we learned back in chapter 7. Some of you may have it memorized already. If you don't, remember that we can always change that into sine over cosine, and then it's a u-substitution. So then it would have been u equals cosine du is going to be equal to negative sine x. And then when we substitute, we need to put in a negative both in front and outside. And then you should be able to see that this is going to become natural log of cosine. And that's it. So x tangent of x plus natural log of u plus c. And then, yeah, plus natural log of cosine plus c. There we go. So are there any questions then with how to do this one? No. Okay. So I believe that is everything that I had. We're doing 2 days of integration by parts. So today was just kind of doing the basics. Tomorrow we're going to get into some of the harder questions. So the assignment, I'm not going to shorten that, but it's only 3 questions anyway, so it's not too bad. And it looks like we're done 10 minutes early. So you all can head out. Have a good day.
Thank you.
Thank you.
Thank
Welcome.
Thank you.
See ya.
Okay.
Have a good day.
Thanks, you too. Bye.